Where's Bertrand? Like, there's Bertrand. He's in Morocco.
Yeah.
I'm not turning on my camera.
That's another really first.
It's all right, Ben. We can imagine you.
So now we start.
Oh, Talia's here. She's all the way 2 hours earlier than me. It's 4 a.m. in Talia's time zone.
It's so early.
Oh my gosh.
So I think we start. No, it's 1 o'clock in my time, 1 p.m. Early afternoon. So hello and welcome everyone to the IGCP 653 2020, zooming into the GOBE conference, 4th day, first session. We have now a selection of 6 talks in the next 2 hours, nice selection of 6 papers. And the session will be like the other ones, recorded. It is already recorded, I see on the red button there. Thank you all for joining us, and thank you for all the speakers of this session. Each presenter will present for 15 minutes. I will, after 12 minutes, give a short sign. There will be 5 minutes of questions at the end of each presentation, and for the transition time then. And please use the chat judiciously, follow the code of conduct in the chat. And I think we can start with the first talk. And the first talk will be by Tomas Želvys and colleagues on isotopes, preliminary report on the Delta 13C isotope excursion through the Silurian of the Jočionys-299 borehole in Eastern Lithuania. So please start, Tomas.
Just a minute. So, I think we have it. Good morning, dear colleagues, or good afternoon in Lithuania, it's 1 o'clock. My name is Tomas Želvys. I'm a PhD student in Vilnius University and would like to do some report about carbon isotopes excursion through Silurian of Jočionys-299 borehole of Eastern Lithuania. The Silurian was the first to have a globally appreciated classification of series and stages, when the present definitions of 4 Silurian series and 7 stages were formalized by International Subcommission of Silurian Stratigraphy. Most evident of these events was extinction of so-called irrevocant event and Mulde event and Lau event. This is a geographical map of Baltica, and during Vendland and Ludlov epochs, the Baltic basin was located near the equator, the south hemisphere. Material about was taken from, as I mentioned, Jočionys-299 core, which is in, of course, Lithuania, and geographically Lithuania is situated on eastern shore of Baltic Sea and lies at the edge of North European plain. From geological perspective, Lithuania is located in western part of East European platform, also called Baltica Paleocontinent. This is the facial map of western edge of the East European platform during the NASA time. All materials was taken from, as I mentioned, the Jočionys borehole. This borehole is located in South Lithuania and represents shallow marine lagoon and sub environments. The Silurian geological section of Jočionys is composed of siliclastic carbonates and sulfitic deposits. Methods. All core samples was taken for carbon isotopes analysis from 235 to 90 meters depth and collected approximately in 1 meter interval. The stable carbon isotopes values analyzed by thermocaster in pair of thermo-isotope ratio mass spectrometry in the Center of Physical Sciences and Technology Nuclear Research of Vilnius University. So about stratigraphy. The Jočionys-299 borehole core can be divided in 5 local formations. So Jočionys in lower part of formation is limestone, and from depth 230 until Paprėnai 216 depth formation consists marl. All Paprėnai formation from 216 to 184 meters depth is formed from clay limestone. The sedimentary rocks also find in lower part of the Jočionys formation, and in upper part of the Jočionys formation, dolomite lays until Verknė formation. In Verknė formation, at the bottom found a little bit of dolomite, which eventuated to a dolomitic marl. Neris and Pabradė formation consist of massive dolomite. In lower part, dolomite is the breccia conglomerate. In the top part of this geological section, we can find some gypsum. It shows that it's shallow lagoon environment. Biostratigraphy. Our preliminary results is that we found 4 biozones of conodonts were identified in that well core. So first zone is Eosteinholm Esses, is found in Pabradė formation and marked Šidolė. CRISPR biozone, which is found in upper Ludlov extincts in Šidolė, and also in lower Ludlov is found Tilmany biozone. And these 2 types of conodonts separates upper and lower Ludlov. Chainwoodian stage is identified with granuliformis conodonts. Here we see some samples of found conodonts, and as I want to mention that at this stage is only preliminary results, and we didn't identify any conodonts in Homerian and in Ordovician stages, and a more detailed biostratigraphic and lithological study is needed to better understand that stratigraphy of Jočionys-299 borehole. I think we will do it in the future. Carbon isotope scale. So according to preliminary carbon isotope scale, sorry for my this will be better. According to a preliminary carbon isotope results, Silurian can be subdivided in 4 isotope deviation intervals in Jočionys-299 borehole. The first interval spans from 234 to 211 meters, and here carbon isotopes values were close to 1 per mile, with some minor fluctuation from the area from 0.39 to 1.44. Carbon isotopes values rises gradually from 0.44 in depth 211 meters to 6.4 promille, depth 188 meter, and then gradually fall to 2.29 promille. This positive excursion can be linked to the irregular weight and the lower Venlo. Additionally, runoliformis content is documented in this interval. So carbon values are moderately stable from 162 to 146 depth and vary from 2.5 promiles to 0.39 promiles. As we see, the fluctuation of carbon isotopes are very big in this chart. So we think that the carbon isotope values vary from almost 9 to 6.4 promiles in the Silurian section, can be related to a shallow marine environment and local peculiarities of sedimental rates. So we identified only Revecan event, and Murdalau and other smaller events can be identified in this analysis. And conclusions. So 4 biozones CRISPR and Nullformis Stankonesis Tilmani of conodons was detected in Jočionys-299 well core. According to carbon isotopes analysis, only Revecan event can be documented, and our events can be detected in carbon isotope score because of stratigraphical gaps. So thank you for attention, and sorry for my face on the presentation.
Yeah, thank you. Thank you very much. And also for being so well in time. Are there any questions at this time? I have one question or two questions. One would be in the Werkner formation. This is all dolomitic and shallow environment. Do we have any sedimentological evidence of meteoric waters or even karst or higher T in that time, so that this negative excursion maybe is related to meteoric waters or something like that?
No, we think that it's sedimentary gaps, and that's why. It's
Okay, good. Yeah, nice to see this from this area, the curve. Okay, I think we have now a little time. 2 minutes. Can wait for the
question.
Any question?
Yes.
Okay, Axel has a question. Good.
Hi. A very nice talk. Thank you. I have a question in your isotope data. So around about 145 meters, there seems to be a big jump in the carbon isotopes. Have you looked at the sediment in this in detail in this interval of the core? If there is any evidence for erosion or something like this?
We think that in this interval it could be some erosion, and because it's only preliminary report, so we will do some more analysis in that well core, because we have a lot of samples, and in the future plans we will do it. Yeah. So is my answer right? There are any questions more?
Quick question if there's time.
Yeah.
Are there any graptolite remains in the core that you might be able to use as well as the conodont biostratigraphy?
Oh no, there's no graptolite in this. It's shallow. Shallow fishes. We didn't find any graptolite.
Okay, see. Thank you.
Yes, we still have a few minutes. Maybe I can ask a question. So your title is preliminary report. So maybe you can tell us what you plan to do in the next months or years.
Yeah, in the next future, we will try to do some climate research, and we will try to research a climate curve, and also we will revise conodonts. In that species where there is no conodonts, we try to find some conodonts.
Thank you.
Maybe I have another question. Is there directly comparable data to the deeper fascias in the Lithuanian and Latvian basins in the Livonian tongue at the moment available? I don't have an overview.
I think at the moment there's no available, but we have only black material for that, so we will do in future, I think, correlations of it. And in 1 year, I think we will have it.
Mm-hmm.
Maybe some more questions?
Doesn't seem like this at the moment. We wait until the next so that we keep in time. We have something like 2 minutes and then, yeah, we will continue.
I can interrupt for a bit and just make some advertising for our YouTube channel. So if you didn't catch any of the previous sessions, or you would like to see this one again, you can go to the IDCP 653 YouTube channel. Please subscribe and like our videos if you like them. Yeah, so you have a chance to catch up on everything that's going on. Notably all the glitches from the admin side, which are still there, but other than that, we have not recorded the breaks. We have only all the sessions.
Okay, wonderful. So we know now. I already wondered where it will be. So now the next talk in a minute or so, in a few seconds, David Harper and colleagues will present this talk about Hirnantian brachiopods in time and space, new insights on an old fauna, very interesting. And yeah, I think in a few seconds we can start.
Well, I'll just start by playing safe and saying hello to everybody. And I'd like to thank the conference organizers. This has been an incredible feat of organization. I think it's an absolutely wonderful way of doing things under the current crisis. I think it's a shame not to meet people, have a beer, have a chat, cup of coffee, but I think it has extended the reach of the conference, and I think that's been a really valuable thing. Now, I'll try and press a few buttons here and see what happens. Yeah. Okay, so what I'm going to do is go back to the end Ordovician extinction event. We're going to go back 445 million years. But for me, it's a bit of a personal journey as well, because I'm going back 45 years to when I sort of started doing research on this topic. Along the way, I've teamed up with Rong Jai Yu, and we've accumulated a few other authors over the years that have been able to do specific tasks for us in this really sort of exciting period of geological time. I'm putting this diagram on, not because it's particularly relevant, but because I really like it. And it gives a little bit of context to what we've been talking about during the conference, going from the appearance of more complex life forms in the Neoproterozoic up into the Ediacara biota, then on to the Cambrian explosion, and then into the great Ordovician biodiversification. Well, I kind of like expansion now. I think that's quite a nice term for it. And moving on through the Ordovician into the end Ordovician or the late Ordovician mass extinction event. This is a diagram from last year. It's probably already quite an old diagram. The speed things are moving at the moment. But this is where we actually did take data from the paleobiology database and just present the raw data against some of these key events, going from the Cambrian explosion, the Ferongian gap, which we've spent a bit of time on showing that this is a gap and data are there to be gathered. The extended GOBE, which in my view, it's the old Webby definition, and it's all things to all people. But there are some very important spikes in there that concern certain parts and certain regions of the world. But then we come on to an area that I suppose is less controversial because it does exist, in my view. The causes, okay, they've been talked about in great length, and I'll come back to that a little bit later. But what I'm going to concentrate on today is basically an update of some work that was done many, many years ago. This is a diagram that I think Thomas will probably talk about a little bit later. I think, yes, it does show this very major event in the Darwinian, but it does show that there is an accumulation of other organisms, particularly in the plankton and the nekton, that have their own individual peaks during the Ordovician. Then we come to the end, the late Ordovician extinction event, where we see this very dramatic drop in numbers of taxa. I think one paper that's really captured everybody's imagination was the Trotter et al. Paper in 2008. And yes, I think it's fairly clear. We've known about this for a long time. There is a very major drop in temperature, and there's a drop in sea level. But Trotter et al. And their colleagues, they focus very much on a sort of evidence-based study on the various isotopes taken from conodonts. Okay, so where did it all start? Well, I think in my view, many others as well, we have to give a huge amount of credit to Peter Sheehan for really stimulating this whole research area. I think Peter's the one on the left there in his Milwaukee museum. And Peter laid down a number of ground rules for really understanding this extinction event. He said, yeah, continental size glaciation, we've got to confirm this and we've got to date it precisely. There has to be a significant lowering of sea level. faunal changeover occurred. It's got to be sort of during or immediately after this glaciation. And also the actual sea level lowering is a eustatic event. It's global, it's worldwide, those sorts of things. I'd like to give some credit to my old colleague, Pat Brenchley as well, because I think Pat and his team in the University of Liverpool pulled together a lot of stable isotope data and correlated this, I think, for the first time against biostratigraphy, against environmental change, and against the actual changes in fauna and biotas through this particular event. Okay, I think I'm staring into the sun there and scrunching up my eyes, as often happens in photographs, but this was really start of my collaboration. I had met Rong Jia-Yu at a conference in Oslo in 1982. A few years earlier, I'd finished my PhD on Upper Ordovician faunas from Girvan. I'd looked at the Folia faunas, I'd looked at the Hirnantia faunas. Jia-Yu was doing the same in South China. Unfortunately, his work was interrupted by the Cultural Revolution, but he picked it up again in the late 70s and was one of the first of the Chinese academics to come out of China and work with colleagues in the West. He came to Galway in 1986 for a month, where I was a lecturer. That was my first teaching post. And we put together the first review of the Hirnantia brachiopod fauna. We examined, reevaluated all the data. We placed the faunas into a time frame. We were able to pull out some depth-related associations, and we established some provincialism in the Hirnantia fauna for the first time. And then we were able to put it into some sort of context between the Catian and the Rhodanian faunas. In those days, you could get away with some extremely Mickey Mouse diagrams in journals, and this is one of my sketches, and which actually makes the point that we have the Edgewood, Kossoff, and Barney provinces, and it's quite graphic, but it's a true cartoon of the time. So what's it all about? Well, it's really a bit of a changeover in brachiopod faunas that's been apparent for some time. The sort of rich faunas of the Catian, including the deep water representatives, such as the Folia fauna, give way to a more impoverished fauna during the Hirnantian, typified by the Hirnantia fauna. My old supervisor, Tony Wright, he was in the vanguard of recognizing the Hirnantia fauna in the late 1960s. John Temple had defined it in 1965, and Tony Wright and Jan Bergström followed that up with papers looking at the faunas in Ireland and in Sweden. And then there was a sort of explosion over the years of new data appearing from different parts of the world to show this fauna. Well, bringing it up to date and work that Christian and I did with Seth Finnegan, we were able to look a lot more clearly at this changeover between the Catian faunas and the Hirnantian faunas in terms of, I think, a risk register, really. And the unexpected thing was that, well, the longevity of the Folia faunas from, well, even going back to the Llanvern in some cases, suggested that these faunas might go on forever, but they were the unexpected victims of this the end Ordovician extinction event. And this work can certainly be taken a lot further to look more closely at different genera and clusters of genera. I talked a bit at the beginning about the causes. I'm not going to go into the causes. There's a huge amount of work still continuing about the causes, but we have over the years identified the ice sheet, the global cooling, the sea level fall. Christian and I did some work on the reduction in the number of terrains, which I think is still very important, and also the role of anoxia and ill-conditioned waters in the deep sea continue to be important. I guess the new kid on the block is the recognition of the possible importance of volcanicity through signals from mercury isotopes within the sediments that would suggest that there are cryptic volcanoes around in the Hirnantian that may have modulated the climate and been a powerful factor in providing a cause of the causes, as it were. But that's an area that is proceeding. I think also the thing that struck me is that there is a phylogenetic dimension or not to the actual event, that if you follow the lineages through, and this is a bit of unpublished work with Leonid Popov and Lars Holmer, and we've chosen a number of talisman sort of genera for the main groups of brachiopods, but you can see that through the Lomi, a lot of these major brachiopod lineages are not disturbed. There's taxonomic loss, but there's not so much phylogenetic loss. And I'd also mention, and again, this is one of my other favorite diagrams by Christian Kröger and his colleagues, the ecological dimension. There's not a huge change. I think Mary Droser and colleagues say, well, it's not really on the scale. Okay, there's a bit of substitution in the community types over the event, but major things like reefs and those sorts of structures don't actually disappear. So it's not a big ecological event. There's also a lot of Lazarus taxa. Taxa disappear, but some of them reappear again in the early Silurian. So there's a bit of work there to really think a bit more about the ecology of this event. Okay, so here we go again. So what did we do? These are some of the usual suspects here. We got the guys, Eostrophiodonta, Paramelamina, Fardinia, we've got a Dalmanella here, Hirnantia itself, Heindella, and over here Cliftonia. And these are the core elements of the Hirnantia fauna. Our entirely new database, we virtually scanned all the literature that we could get hold of. Our own personal experiences, field collections over the last 15 years. Data from 20 paleoplates. We looked at all the taxonomic assignments and we re-evaluated those. And we looked at the stratigraphical correlations and associated facies. And I didn't add here, but there's a huge amount of work has been done on paleogeography that we were able to include in our study. And so new taxonomies, new stratigraphies, and new paleogeographies. Huge amounts of data from South China, absolutely incredible stuff. And we're able to learn so much from the South China plate about the distribution in terms of facies and in terms of time in the Hirnantia fauna. Now, stratigraphical control, and I'll buzz through these, but this is to provide some sort of assurance as to the level of detail that we went into, that we assessed all known sections with these faunas. We precisely dated them according to the graptolite and other zonations at the time. And we developed quite a detailed overview of what's actually happening. We were able to look quite clearly at changes in terms of the taxonomic groupings through the event, and actually look at the diversity changes at the generic, family, superfamily, and ordinal levels. It's a little bit misleading because in the middle part of the curve here, during the second phase, there's actually a series of new taxa appear, and this is something I'll come back to that's been quite interesting in this particular study, that during this time of crisis, there is speciation going on. We were able to develop this rather fine diagram, which I think says it all. And we can look at the appearance of the Hirnantia brachipod fauna with this turnover from the various mid-continent and shelfal and deep water faunas in the Catian to a diachronous appearance across the world of the Hirnantia fauna. In deeper water, we have the Aegiromena fauna, and in shallow water, we have various associations dominated by Whitfieldella, Plectothyrella, Hindella, those sorts of things. So we now have a pretty good handle on the time and place of the appearance of these faunas. I'd also mention that we've created a new term, the Edgewood Cathay fauna, for the survival or the subsequent radiation within the upper part of the Hirnantian. The huge scale of the work, I think, is apparent here in that we identified all these areas throughout the world dominated by typical, atypical Hirnantia faunas, and then the Cathay Edgewood faunas subsequently. We've applied a number of new methods to analyze our data, and this is network analysis. And I've sort of moved away from cluster and ordinal techniques. This, as many of you know, is the type of analysis that Facebook uses to look at social clumps of people, and why not look at it for groups of brachiopods? And this has been quite effective in defining the Hirnantia fauna and the Cathay Edgewood fauna. In space, we've been able to, again, really focus very hard on the environmental distributions of these brachiopods, almost being able to determine communities in the Ziegler sense, from shallow water to deep water. And so I'm going to quickly summarize now what have we found out that we didn't know before. I'd emphasize this at the bottom up. It's not a database, a paleobiology database. It's go back to the original data, assess everything very carefully, and use these data to establish our understanding and models. We've reevaluated the Bani, Kosov, and Edgewood provinces. We've now discovered that the Edgewood province is slightly younger. It is late Hirnantian age instead of early to mid Hirnantian, and so it's subsequent to the main development of the Hirnantia fauna. That means, however, that the Hirnantia fauna itself has a near global distribution, which is quite remarkable in the whole of the Phanerozoic, that this group of brachiopods is so widespread, almost, well, from the poles onto the margins of the tropics. It occupied a very wide range of depth zones. I think the later Hirnantia faunas, the Cathay, the Edgewood faunas, there's still the possibility.
There are 2 minutes left, more or less.
Absolutely perfect, Björn. I'm right on time. And you can associate those with siliciclastics and carbonates. I mentioned very briefly, there is speciation occurring during the crisis interval. And during the Silurian, we're looking at that sort of takeover that we've known about for a long time, that we've got the aethyrodids, the atropids, spiriferids, pentamerids are moving in to take over from the orthides and the strophomonids. And okay, it was a big extinction, but suspension feeding benthos survived, and they dominated the marine benthos for the next 200 million years. So thank you very much.
Thank you for this wonderful overview. We have like maybe time for one question.
I have a comment that, if I can just add, I think it's a fantastic job, Dave. And I think this thing with actually tracking how the facies, how the faunas are changing across facies through the Hirnantian, that's really a milestone. So yeah, thumbs up from here.
Yeah, well, thank you. If people want to read more, there's a ESR paper on this, and I hope I might embarrass Christian, but he gave a superb review of the paper and made some very, very positive comments, which we followed up on. So thank you for that.
It was a good paper.
Wonderful. Okay, we have to move on. Richard Hofmann gives the next talk, and he will hopefully answer the question why there was no GOBE in Western Laurentia. Maybe there was a GOBE, we will see. Okay. Go.
Can everybody hear and see me? Okay, looks like that. Okay, hello, welcome everyone. I'm particularly delighted this is my first virtual meeting, and so far I like it, and thank you very much for Christian and Alicia to putting this up. So, why was there no GOBE in Western Laurentia? So this is a picture of Western Laurentia through some recent time towards the Ordovician. Okay, and what this IGCP project is concerned is when was the GOBE, so when did it start? And if we look at, old graphics, this is not the most recent diversity curve, but I usually start with it as an icebreaker. It's the oldest diversity curve we have from Phillips 1860, and the GOBE is exactly here, I guess. And if you look at more recent data from Allroy et al., which is the most highly cited Phanerozoic diversity curve, it's still, so it hasn't changed much. So here you see the Sapkowski curve as well, and Allroy's curve, and it's still a steep hike in diversity, which is not very well constrained in time. And this is where I started when I drafted the proposal for this project. Okay, I wanted to get a grip on where it is. And then in recent years, like last year by from Christian and Alicia Stigl and Björn Kröger, based on a lot of data all of you guys contributed to, it appeared as though the GOBE is pretty much confined to a time frame, which is the middle Ordovician, and the steepest hike in those global compilations comes up from, if you look at the Depingian and early Derivillian time interval. This is where you have a diversity hike that is unparalleled in what becomes before and after. So even the Cambrian explosion is apparently, it's an ecological and evolutionary event of this scale. So we see here, this is based on data from Dave Harper and Christian Rasmussen as well. We see the different brachiopod families, and the main GOBE phase is also pinned to the Derivillian. And there's this pre-GOBE phase where something happens, but who knows what. And yeah, so this is the starting point where we want to look at the GOBE. Okay, and this is the Pogonip group. This is the a picture of how it looks in the field. Is superbly exposed in Western Utah and in Nevada. Here, I don't know if you can see, there's a person for scale. So this is approximately like 150 meters of the Pogonip group as an example. So this would be the Calathium calcisiltite member and the little bit of the Wawa formation on top. So these are world-renowned outcrops to study throughout whole of the Tremadosian and the Florian, and so essentially lower in the middle Ordovician. And it's essentially a shallow marine record. So it's on shelf, it's not too deep, and this is where you start to find fossils. And in fact, it's one of the most fossiliferous and most continuous records of lower Ordovician life. Okay, and this is where I started. And if you superimpose this diversity curve from, I guess it was from Björn Kröger on this, like very coarsely, don't bring me up where those wiggles are, but it should happen if the global signal is real. It should be observable around here. So the Juab formation, the Kanosh formation, and the Lehman formation. This is where you should start seeing things getting diverse. And when I first started, my first field season was, I stumbled across these hills and cliffs there in the Ibex area in Western Utah, and I thought, shit, this is a lot of rock. And I started in the Kanosh formation because essentially it's so fossilifer, it's very easy, it's very juicy. So you can sample like through the whole day, and this is what we did in the first week or so. And just a little bit of geological background. So Western Laurentia is situated right across or right below the equator at Western Laurentia, of course. There's a more local map where you see in Utah and Nevada, and there's much dispute on if there was a thing like the Tueli Arch. This is a land positive area which some sort borders this Ibexian shelf, which stretches from Utah to Nevada and gets into the deeper marine realm in western Nevada. Okay, so if you look at these Canoche and Lehman Formation, which are the youngest fossiliferous units of the Pogonid group, they look like this. So this is the famous fossil mountain. It's a world-renowned locality to look for Middle Ordovician fossils, and the Canoche Formation mainly is a silt and shale interval about 150 meters thick or so, 120 meters. But there's intercalations of limestone, and the Lehman Formation is a little bit more resistant, so it's marlstone and dolomites. And then you have it's whole capped by the quartzite, which is essentially the Ordovician coastline by that time. Okay. So this is where we started sampling. So, and we counted the fossils, we determined all the fossils that were determinable and or identifiable, and then we had a beautiful abundance matrix, and we run a lot of or some multivariate statistics on it, like NMDS, non-metric multidimensional scaling, and cluster analysis to see if there are recurrent sets of species. So this is the classical approach that Dave Harper discarded for this network analysis. I should try this too, maybe. But anyway, so this is what we came up with. So the Canoche system is, in terms of diversity, pretty low diverse. So you see here, these are different groups. The green things are the brachiopods, the red things are the trilobites, and some other most notable fossils in this Lehman Formation are leoparditicocopids, which are some sort of ostracods, like large shelled arthropods that I think just have been kicked out of the ostracods. I'm not sure. Anyway, so what you see for most of the Canoche Formation, it's a very boring fauna, which all the same species occurring in whatever fascies you are in. And there's subtle difference. So the cluster analysis did not very well reproduce anything, but this is what we came up with. So there's a slightly higher diverse. We see 8 species, and there's 5 species and some 7 species. So it's not very diverse. Of course, there's more. You see a lot of crinoids, but it's and a lot of echinoderms, and of course a lot of bryozoans. But from a quantitative perspective, it's not easy to quantify, and it's not easy to identify them, especially the echinoderms, because you just find debris. So this is just good enough for me or for us by that time. But the take-home message is that it's not very diverse. You have a very recurrent set of species throughout the whole formation. And this was the time where actually the GOBE should start. So where's the GOBE gone? And if you look at this is how we reconstructed the paleo environment, essentially. So you have a gradient from, this would be the coast. It's pretty sandy, a lot of the siliciclastic stuff coming into the system. That's why it's so shaly and so silty. Sometimes you have some prodeltaic deposits coming in, which signals there's a source for these siliciclastic deposits, and they of course mess up with the fauna essentially. So benthic filter feeders don't like being confronted with a lot of silt and a lot of turbid water, and that's why I think is the best explanation for this fauna to be rather low diverse. There's some, the highest diverse fauna is this one, the number 3 here. This is where the trilobites are. So they apparently are confined to those outermost regions of the basin, or the deepest part of the basin. And but there's still, you find all the other brachiopods still. So it's not, these faunas or faunules are not confined by the presence of things, but rather by the absence of something other. And then it passes into the upper part of the Canoche Formation, becomes the siltite member, and then comes the Lehman Formation, which is essentially a lagoon, which is intertidal and supratidal, and it's mainly marlstone and dolomites and carbonates. And it's pretty shallow and it's pretty stressed. So that's where your GOBE goes. And then the Watson Ranch quartzite is, of course, the delta and the tidal plain just behind the sea. Okay, so this was the bummer for this one. And so, but of course, this project focused on the whole Pogonip group. So we go just more back in time, and this is the Wawa and the Juab formation, which just straddle the lower and middle Ordovician boundary. And this should be interesting, of course. So, and we did the same thing with this quantitative paleoecology thing. We did it there. And this is where some other stuff happens. So here, unfortunately, I just saw this. This is now coded according to these associations, if you will. So the different colors give you a sense of the associations. And there you see, first of all, that there's quite some diversity in the brachiopods and in the trilobites as well. So these lower beds are dominated by these Hesperonoma diparallesma association. And this is up to 14 species, I guess, and it's mostly dominated again by trilobites and by brachiopods, and the brachiopods almost all belong to one family, the Hesperonomids. So which shows that there apparently is some GOBE going on, because the GOBE, almost by definition, is an aggregation of diversity in lower systematic levels, like within the family, several genuses within a family being diverse. So this is what we see here. Then this big line here would be the Phloem and the Pinguin boundary. And this is where we have a huge turnover in the species. So the brachiopods all disappear. I wouldn't say they go extinct really, so there's some overhang, but they at least disappear within this basin for the remainder of the Pogonip, and then it changes. And then you have this Orthambonitis superlata, which is a very easy recognizable brachiopods in the Juab formation. And you change also the the trilobites, not so much here on the genus level. So Pseudomera also occurs further up. So, but and down below as well. But what you see here is a huge turnover and the rather low diverse fauna recorded in the aftermath of whatever happened here at the boundary. So, and this is essentially what I have to tell you for now for the Wawa-Juab system. But the sedimentary environment is much more open marine. It's probably not as stressed in terms of siliciclastics. And you have beautiful mounds there, crinoid mounds, sponge mounds, just below the wave base. And inner shelf environments are dominated by calcareous debris, by bioclastic debris, and so on. So this is a normal marine environment. It's probably not as encroached by land masses or whatever by that time. This is why we think it's much less stressed and much more hospitable to normal marine fauna. Okay, the Pogonip summary then would be that we see this diversity decline towards the Phloem and the Pinguin transition. There's a huge turnover in my sense at the boundary, and we see these really impoverished faunas in the lower Juab. What's significant, I think, is that we lose a diverse family of brachiopods, which some sort gives an idea of that there is a reset of an actually GOBE type fauna, which you see in the upper middle Ordovician and the lower upper Ordovician. And we think there's a stress communities into the Pinguin, the Rillian for the remainder. And this pretty much is why there was no GOBE in that sense, in the sense of Rasmussen and Stigger in recent years in Laurentia and Western Laurentia. So it's just not the right time or the right place rather to search for the GOBE apparently. So, but we have to stress, is this a global signal? So do we take that? And there's, if you look at this diversity trajectory throughout the Ordovician taken from Rasmussen et al., so you see there's a low, it's going down in the course of the Lithuanian, and there's a Lithuanian and the Pinguin also, but it doesn't show up in global compilation. That's why I think we should do these local studies to really, this is where you see how the ecology functions now. So, but there's this record from Baltica based on work by Christian Rasmussen as well. And the green stuff highlights what I see as well. So we come here from fairly diverse communities if we just length this out for a minute. So there's a reduction of 50% of diversity in the brachiopods and the high extinction rates in the brachiopods. So it's just dwarfed by this immense hike you see then for the rest of the remainder of the middle Ordovician, right? So if you just see that, we would say, well, it might be a local extinction or what. And then you see these, going back to rather low diverse communities And this is a whole lot different. The red stuff, this is where you would see the Canoche formation in terms of stratigraphy, but it isn't because the Canoche formation is just a nasty, muddy, hot bathtub in a way. Okay. So what could cause, and yesterday, I think in the session, we saw a lot of evidence for that the Ordovician Ocean is some sort of, let's see, the lower Paleozoic Ocean, some sort of different, so that you have a default mode of anoxia that linger just below the shelf edge. And whatever happens when you change the system, you change the temperature, or you have in transgression, regression cycles, these anoxic waters can impinge on the shelf and kill off and this is what we see here, kill off the immobile fauna, okay? So in all these little wiggles here in the carbon isotope curve presented by Colette and colleagues, you see these, or at least what I understand from these papers is that these positive shifts that occur from time to time could mean an enhanced burial of like carbon, which could be or is most easily explained by anoxia. Okay, and these, yeah, it's not very good, but these happen around the time interval, to say the least. And then all of a sudden, the system goes towards more negative values, which has some greater implications. Okay, but I would say that until here, this is time interval. So we have this default lower Paleozoic hostile ocean, which kills off your benthic immobile fauna. And this is why the brachiopods are so, they just come in full swing from this time interval. So this would be my best explanation for now, but I'm happy to take, to discuss over this. So why is there a sudden GOBE? My answer would be this is oceanographic change and the release of diversification of these typical GOBE faunas, like the brachiopods, the immobile fauna, the echinoderms, and so on. And this long recovery is, or of these faunas that react slowly to these pulses of extinction. This gives you the low diversity interval being part of the, which is typical seen in the lower Ordovician. And so what I actually wanted to do, and what I will do still, is competition. So it's look at intrinsic aspects. So is there competition going on? And so this would be an alpha, beta, gamma diversity story, which I'm pursuing within the next months. And the next project really is taking bioturbation data into account, because I think the bioturbation story is gives a lot of answers of how we should interpret geochemical markers and preservation potential for our fossils. So, and that's it. And I'm happy to take questions if there's time. Thank you.
Yeah, thank you for this wonderful talk and to get an insight on the idiosyncrasies of regional diversity curves. Are there any questions at this?
I have one. So Richard, this is really interesting. So what, so the general story that you've got of, this bathtub related to chemical changes, and then of course seeing a very different pattern than what is present in the mid-continent and the Arbuckles, where we have a pattern that matches Baltica pretty clearly. So I think that's really exciting, thinking about those kind of differences in that regional setting of having that kind of basin with the deeper water nearby, having that rather different pattern than what we see in the middle of the continent. So thank you for sharing. That's really very cool. What is your kind of thinking about the difference in those regimes? Was that kind of a similar take to what you were thinking, or what were your thoughts about the Arbuckle section relative to yours?
I think it's just for this time more open marine. I guess I haven't seen it. I know that I asked you to contact your master student. What was the name?
Sarah Truvitz.
Yeah, exactly. Or I asked you if we could do something to compare this with, actually. So I mean, the Pokémon essentially runs out of data right when it gets interesting.
Yeah.
So yeah. So
that's really cool. Yeah, the curve is back in the geology paper that.
Yeah, I know. Yeah.
It certainly seems like there's a big basis component to this event, that's for sure. So I also think it's really interesting to see your data.
Yeah. So the Baba Juab paper is going to be submitted soon, I guess. There's just some photographs lacking that I couldn't take because of the lockdown of the museum. So, yeah. Well.
One extra. Of course, with a lot of ecosystems, you have a big disparity between some that are dominantly sort of shelly taxa and others that are dominantly soft-bodied. So given that we're only seeing sort of one part of it, you're talking about preservation potential being something you want to look at. I don't know if there's any way or any potential for looking for SCFs or small organic fragments that might tell you if it was just a different community which is dominated by not normally preservable groups.
Okay. Yeah, that's an interesting point. The problem, or what I usually say is I look at the soft body, then you get the whole picture. I said, but I would say, if you look at these global data and these beautiful diversity curves, it's mostly based on these shelly fossils anyway, right? Yeah. So it's like, there's an error, but at least it's on the same thing. And what I mean with preservation potential is that when you go through the pogonip, the lower part of the pogonip is almost never really bioturbated in that sense that you have like a fully bioturbated soft bottom. And this is the time where you have this really finely churned trilobite sclerates. And I think, okay, if the sedimentary upper surface is just firm, why should the trilobites be deposited there? So they just get bypassed through the system. So, and this is what I would think affects the preservation potential and hence the distribution of fossils in space and time. So this is
okay. We have to stop here.
Yeah. Okay, sorry.
Yeah. You can continue in the breakout.
Yeah, cool.
Okay, very interesting. I also have questions, but anyway, we have to continue with the next talk. Bertrand is the next, Lefebvre and colleagues. The great Ordovician diversification of echinoderms now, deciphering the complex global signal.
I think you are muted, Bertrand. Just click the microphone in the lower left corner.
Well, it's okay. Yeah.
Ah, we hear you now, I think.
Okay.
Now you can start again.
Okay. So here we are. Okay. So hello, everybody. So echinoderms. So echinoderms are a very important group of marine invertebrates, as you know, especially in modern faunas. They're a major component of ecosystems with a bit more than 7,000 taxa today. But they are also very important, of course, for food, because it's lunchtime now. Well, not only in France, but also in China. If we look at modern echinoderms, they are represented by only 5 classes. So you know ophiurids, sea cucumbers, crinoids, sea urchins, and starfish. But that's very little compared to the diversity of the group in the Paleozoic. In Cambro-Ordovician times, we had 17 more classes, so much more than what we have today. And especially in the Ordovician, we had the highest diversity in terms of disparity, morphological disparity, with 19 classes in the Ordovician. So if we look at the
I'm sorry, I think that now we, at least in my case, the screen is kind of frozen. We see still the first slide only. Mm-hmm.
Okay, I don't know what happens. Is it okay? Do you see anything? No.
The first slide. It's just at least what I see.
You see the next one? Non, not yet. Ah, attends, qu'est-ce qu'il y a dans le partage en pause? Faites passer sur le dessus votre fenêtre partagée. C'est quoi ce link? Reprendre. Ah.
Can you click the arrows in the lower left?
Ah, yeah, yeah.
2 minutes left.
I remember I saw already the honey, but now at the moment we only see the great order, the opening slide.
And here? No.
There are. Oh yeah. Now there is a sea cucumber.
Ah, so it was the food slide. Okay, good.
Yeah.
So I was showing the it was the modern ones, the past ones, Paleozoic ones. So it's okay. Can you all see everything? Yeah. No.
Yeah.
Yeah. Okay. So just saying for echinoderms, it's almost the same story as for all the groups of metazoans. If you look at very large scale, they're appearing in Cambrian series 2. They're already diverse with 4 classes. That's the number of classes. There is a huge diversification going on in Cambrian series 2 and 3 with 7 classes. A small extinction here with losing 1 class. They keep diversifying slowly in the upper Ordovician, in the upper Cambrian with 2 classes left. But there is something really huge getting in the Ordovician. We have 6 more classes appearing in the lower Ordovician, including crinoids. 6 more classes again in the middle Ordovician, and just 1 more in the upper Ordovician. So that's a very big picture of diversity. Of course, they're strongly affected here by the late Ordovician extinction event. But usually when new classes appear in the fossil record of echinoderms, they are, for example, if you look at crinoids, they're appearing here in the lower Ordovician. We have almost all the main groups of crinoids which are there, but each is represented by a limited number of taxa. And most of the family and generic diversity will appear later on. So what have we done? We've reused and updated the data set we had prepared for the big book in 2013. So around 4,000 occurrences of echinoderms in the Ordovician, around 2,000 taxa. We have updated it. We have included all the most, or as much as we could, new occurrences published in the meanwhile. We could have used PBDB. We've been hesitating to do it. It's almost the same quantity of information in there, but we had some problems with some data. For example, if you look at Sandian echinoderms from North Africa, there's just nothing in the PBDB, although it's a hotspot with more than 40 or 60 different species there for many occurrences. So we prefer to stick with our own data, which have been fueled by all the colleagues from different continents by published and non-published evidence. So we prefer to keep with that. It's not too bad. So that's the global picture we get for echinoderms for the whole Ordovician. So it looks very similar to what we have for most groups of metazoans with a relatively low diversity in the beginning from the Tremodocian to the Dipingian. It could be a curve of brachiopods or anything like this. Then we have a rise in the Darwinian, a peak in the upper Ordovician. So, okay, it's very standard signal, it's fine. But if we look at the evolution of the various groups we have in there, indeed, most of our peak is due to these guys in green, the crinoids. It's mostly a burst in crinoid diversity. If you look at other groups, for example, Rhombiferans, one of the major groups of echinoderms, which contribute to 16% of our data, well, there's a regular increase. We have a kind of plateau in the late middle upper Ordovician. It's even a larger plateau. If you look at Diproperans, it's beginning very early in the middle Ordovician. There's no real peak nowhere. And if you look at Asterozoans, yeah, they're a bit more diverse here, but there is nothing really significant. And it's even worse if you look at other classes. In Stalophorans, it would be, for example, even more diverse early on and decreasing. Of course, we don't have enough data to compare if you look at eocrinoids, paracrinoids, but we don't have peaks in any other group of echinoderms but crinoids in the late Ordovician. So that's mostly a peak in crinoid diversity. If we look now at the regional pattern, So we've plotted that's the cumulative curves. It's almost the same. For example, most of our peak here is due to these ones, which are the Laurentian data. So what we have, if you look at the Laurentian faunas, they contribute to about half of our data. The diversity remains very low until the late middle Ordovician. Then we have a huge diversity peak in the Sanbian Cation in Laurentia. And as you can guess, it's due to diversification of crinoids. If you look at other regions, if you look, for example, at high latitude areas of Gondwana, we have already quite high diversity early on in the early Ordovician. Then we have no data at all in the Dapingian. And then we have a more or less plateau during most of the middle and upper Ordovician. It's about the same for Baltica, no data at all for the early Ordovician. And then it's a plateau for me. There's no real peak in there. Avalonia, it's even worse. We have very few data up to the very, very late Ordovician, where there was a small peak here. And for other regions, we don't really have enough data to say anything. So the peak we have in echinoderm diversity is mostly a Laurentian peak, which is due to diversification of crinoids, clearly. So if we look at now through time and space, what happened? So here you have a kind of a global composition of all echinoderms from everywhere in the world put together. And here it's split by region, big areas. So that's Laurentia, East Gondwana, and South Gondwana. Clearly, most of our data come from two regions, mostly from Laurentia and two areas in South Gondwana. And in all areas in the lower Ordovician, we have diversification of endemic, mostly endemic faunas from the same original low diversity Thuringian stock. We have here this Laurentian fauna, which is dominated by crinoids and by eucrinoids, by edriosaurids, which is relatively isolated from what we have in other regions. And we have huge diversification here with different taxa in high latitude regions of Avalonia, Morocco, Montagne Noire, and so on. And these assemblages are dominated by stalophorans and eucrinoids. So we have very contrasted faunas already in the lower Ordovician. In the middle Ordovician, it's getting even worse. We have more data that's better, but we have getting very endemic fauna, much more than in the lower Ordovician. So we have four areas where we have a relatively good record, and they are very, very distinct from each other. So for example, the Laurentian fauna is clearly dominated by crinoids and edriosaurids. We have in all these regions here very similar high latitude faunas dominated by diproporans and stalophorans. In a low latitude Gondwana, we have mostly cystoids, so rombiferans and diproporans, and another group of cluster of taxa in Baltica, where we have new taxa originating. For example, the oldest echinoids and holothurians are appearing in this time in Baltica. That's unique in this time. And things are really changing a lot in the upper Ordovician. So interestingly, if you look, in the middle Ordovician, our signal was mostly from Baltica. It's where the region where we had most of the data, but it's not too bad here too. If we now move to the upper Ordovician, most of our data are from Laurentia. We have very few data from other parts of the world. And we have much more cosmopolitan, much more exchanges between the faunas. For example, we have two of them here. In the Sanbian, we have invasion in North America, in Laurentia, of taxa from Baltica. Those are the first echinoids, for example, arriving there, and also from high latitude regions, for example, stalophorans or solutians, they are appearing for the first time in North America. We also, that's so from the south to the north, but we are also what we call the Boda event. We have it for echinoderms along the margins of Gondwana, within the Cation, invasion of temperate faunas from low latitude Gondwana towards high latitude regions. So change in faunas. But clearly, if we look at the composition of our faunas in the upper Ordovician, we have two different worlds. We have a Laurentian world, which is dominated by crinoids, and a non-Laurentian world, which is dominated by rombiferans and diproporans. It's completely different in terms of composition of the assemblages. But we have much more data from Laurentia, so it's completely squashing the signal. So it's why we have so many crinoids. So we have very different regional patterns in the Ordovician for echinoderms. We are lacking data for most areas. We have almost clearly not enough data from South America, Siberia, Central Asia, from Africa. That's clearly where we're lacking data for many areas. It's quite good for, it's excellent for Laurentia, of course. It's not too bad for Avalonia, Baltica, and most regions of Mediterranean regions, but it's not that good. So what we get, our global signal for echinoderms in the late Ordovician, and in particular this late Ordovician peak, it's mostly reflecting the diversification of crinoids in Laurentia. So it's not for me a global signal. And we have no obvious peak in the late Ordovician in other areas. Voilà, that's it. Thank you for your attention. And sorry for the technical problems in the beginning.
Thank you very much. This was fascinating and interesting. Again, more details now we have for the GOBE. Any specific questions at this moment?
One if possible. Okay. How much of the patterns do you think can be explained purely through particular taphonomic windows being available in particular regions, like of course the carbonate platforms of Laurentia versus the starfish bed at Gervan, which I imagine is quite a lot of the diversity of the Avalonian in the late Ordovician.
Yeah, that's clearly that's one of the big problems, of course. Echinoderms, especially Paleozoic forms, Ordovician forms, are mostly easily degradable taxa, so they can be disrupted very easily. So the more Lagerstätten, Echinoderm Lagerstätten will have, the most windows will have to get some fauna. And there are lots of them in North America. And now we are improving the situation. We are getting more and more Echinoderm Lagerstätten in other regions. So we have new findings in Bohemia, in North Africa, in many other regions. So hopefully that is the way to move forward and to get more data. But we still also have to do it in other regions, because if we lack echinoderms, it's because they are not preserved. In any marine environment, they should be there. But as they are very easily disarticulated, if we don't have the good taphonic conditions, we never find them, or just pieces, ossicles, and it's difficult to make sense of them. Yeah, clearly. There's a taphonic bias. Yeah.
Okay. Thomas is sitting already in the start holes. Thank you for the discussion.
Thank you.
So the next talk will be by Tomas Želvys and colleagues. Early Paleozoic diversification, explosions and events, or a continuum of change.
Can you see me? Can you hear me?
Yes.
Okay, so it's also my first time here doing this on Zoom, so I hope it will be okay. So I will ask today a question that is old and give an answer that is maybe new. So do we have several events or explosions, or is it just a single diversification that we have all over the early Paleozoic? This figure, you have seen it already. We published this 10 years ago. Björn was involved in that one too. So here you see the succession of different events, like with bombastic names, like the Cambrian explosion, the Ordovician biodiversification, Necton revolution. There are others like agronomic substrate revolution. We will hear about the Ordovician bioerosion revolution. There was a plankton revolution. So a lot of revolutions happening. But is there really space for an explosion? Was there really an Ordovician event, as the different curves suggest or may not suggest? So we try to answer to that question. Actually, we did this in the paper that was published earlier this year in a special issue, memorial issue of the Geological Magazine. So you can find as a paper there. There will basically nothing new today, because this is recorded and we are of course not showing all the unpublished things. So is there an explosion, an event, or is this all the same thing? This is a question of point of view. This is a question of the techniques that you use. How do you get your pictures? So there's a question also of the evolution of the techniques that you use, the evolution of the camera. So we already have the, Richard showed us the figure of John Phillips. He was with very old machines. He was just counting the different groups through time, and he came up with the first biodiversity curve. Then those who are a little bit older remember these things from the 60s and 70s. So this was a pocket camera. And this is about the machine that Jack Sapkowski was using when he took the pictures of his biodiversity. And I don't comment this curve. You all know it from your first days in university. About 20, 30 years later, we all moved in the early 2000s to digital cameras. Oh, high resolution, lots of pixels. And this is what we did with, for example, the paleobiology database. And here you can already see a completely different picture. Now, we are no longer with Sapkowski's different points. So here you have a long-term radiation. But when you are playing with digital cameras, you know that you have pixels, you can upscale, you can downscale, you can change the pixels, you can do a lot of these things. And this is what Alroy also did. So if you look at the red curve, this has almost nothing in common with the blue curve. And these are the same data. These are the same data, but used differently with different pixels used. And here for the Ordovician, in the red curve, you see a clear Ordovician radiation. But when you look to the blue curve, when you have corrected data, you see a long evolution from the Precambrian to the Devonian. So have we an Ordovician event? That's simply a question of view. It depends on the questions, on the techniques, on the machines that we use. First of all, let's remind us why we call this a Great Ordovician Biodiversification event. Why this is called the event? This is because one of the previous projects, IGCP 410, was proposed in '96 by Barry Raby, Florote Paris, and Mary Dwoser. And they called this, to get some money, they called this a Great Ordovician Biodiversification event. Why they did this? It's because in '96, if you wanted to get some money for a funding agency in geology or paleontology, if your name event, the word event was not included, it was very difficult to get any money. Otto Walliser published the famous book, Global Events and Event Stratigraphy. So this was a time of events. Do we have an event in the Ordovician? Do we have an earthquake, a tsunami, or a meteorite? This is a question. We are still looking for this kind of events. So do we see an event? It depends on the techniques we use. We can use filters, not only for photography, but also if we look to our paleobiodiversity data. You have the color filters that you can use as taxonomic filters, for example. You have also different gray filters. You can play with taphonomic filters. You can play with geographic filters. And we have seen from the previous talk that depending on where you are, you have different pictures. And the filters are very useful when you want to show something that in the original picture you don't have it. So if we use taxonomic filters, for example, if we use a brachiopod filter, here we have an event. It clearly pops up. We clearly see something. And if I would be a brachiopod worker, I would say, wow, what is happening here? In the middle of the Oanic, at the base of the Middle Ordovician, something happens here. There must be something, there must be an event. Now there's something more that comes with modern techniques. You all know this, it's Photoshop. So once you have your picture, you can modify it. And this is what these people did. Here they used, if you read the paper, they talk about major biodiversity pulses. And everybody is saying there were major biodiversity pulses. But if you look in detail to the literature, they were not exactly here. This is what we did. And the chairman of this session was included in that paper as well. We did this with the different fossil groups, and we were trying to find out where have been the major biodiversity pulses. They were all at different moments, at different times. If we look just shortly to other data sets, this is probably the most complete data set on graptolites published by Crampton et al. And PNAS. And here you see that the onset was probably, the major onset of the graptolites was in the Florian. The brachiopods, we have seen this, was somewhere in the Derivillian. And now if we move to the reef community, so this is by André Ernst, the most detailed database on bryozoans. The major increase is somewhere here. This is what led us to publish this paper saying that the Great Ordovician biodiversification event, or the Ordovician radiations, as mentioned from the beginning by Sepkovsky, are very complex, with different things happening at different moments. Now we have this, and very few people mentioned this during this meeting, which is fairly surprising. We have seen it yesterday, but not used by a paleontologist. We have seen it by a geochemist. And what you can see here, these are the Chinese data. This is not PBDB, but GBDB. And in GBDB, we have a very strong increase of the diversity, but this starts in the middle Cambrian and stops in the middle Ordovician. Actually, when Richard Hofmann was looking for his GOBE in Laurentia, well, he was just in the middle of the biodiversification when we have it in China and elsewhere, because geobiodiversity database is also a global database. We shouldn't just say this is just Chinese. And even if it's just Chinese, it would say us that we have a completely different picture from China that is not the same as in the PBDB. And this is simply due to geography. We have a lot of data from Baltica, and we have a diversification in Baltica when Baltica moved northwards during the Ordovician, when it moved into tropical waters. And in tropical waters, we have biodiversity hotspots. In China, it was earlier. In Laurentia, it was later. We clearly have a geographical trend. But today, I'm not talking about this. Today, I show the different taxonomical filters that we used. So we tried to go to different data sets, and we looked to the taxonomic filters for different fossil groups. By the way, here I show you another figure that is not yet published. I thank Peter Sadler from Riverside who allowed me to show it. This will be published in chapter 20, the Ordovician period of the geological timescale 2020, in a paper by Dan Goldman, who provided me the picture. These are extremely good data sets for graptolites, conodonts, and Chitinozoa. You see the number of sections involved. And you see that the onset of the conodonts was much earlier than that of the graptolites and that of the Chitinozoa. So we have different scenarios here. This is what we tried to do in the GeoMac paper. We went to all the fossil groups available. Here we have planktonic groups like Arquitax, Chitinozoans, Radiolarian, graptolites, polychaete worms, and fishes have been added here. What is very important to note is that there are no Arquitax data in the PBDB. There are no data on Chitinozoans on the PBDB. There are no data on polychaete worms in the PBDB. And if we look in more detail, you have just seen this, Bertrand showed it. These are the PBDB data for graptolites. The database in the PBDB is not as precise as that by Crampton et al. We have the same pictures for trilobites. The database by Jonathan Edwain is much better than that in the PBDB. And this brings us to a general remark. I cite here another person that is not involved in our meeting. I just found this in literature. But this is about North American fossil mammoths in the database. And Dan Protero from Los Angeles just said, if you put garbage in, you will get garbage out. We have to take really care about what we are doing with our databases. So if I continue with the different groups, so I have not the time to talk about all groups. Here we have brachiopods, stromatoporites, bryozoans, and you see always different scenarios, different curves. If you apply different filters, you have different GOBEs. Every single fossil group can say, here is my GOBE. So we did this for bivalves, ostracods, conodonts, cephalopods, trilobites, which is a very complex group, gastropods. And then we also try to play the game and put this in different groups like plankton, dectobenthos, nekton, fixed benthos, mobile benthos, reef builders. And this is very tricky, as we have seen yesterday about the talk about plankton, the nekton revolution, sometimes it's impossible to put the groups in a box because some have complex life cycles. They start planktonic and they end up at fixed bentos. So it's very complex to put all this together. We also put this, of course, in a general database. So here you have the PBDB data. And so you can see a Cambrian explosion, and you can see an Ordovician radiation. And this has clearly 3 steps. Maybe China Gondwana, maybe Baltica, maybe Laurentia. So it is a succession of things. If you compare this to strontium isotopes or other isotopes, very difficult to find something. Maybe here was an event with strontium isotopes. Difficult to say. And now to another remark, other people who also work with the paleobiology diversity, and please note John Alroy is co-author of this paper. So these people in a paper earlier this year, 2020, in Proceedings B, they published and they say that also the diversity patterns for regionals at regional scales are very good. At the global patterns, they make no sense because there are too many holes. We have patchy information, and so the global estimates for tetrapod diversity is so far not possible because we don't have a good knowledge of our fossil record in total. So we have to think about this. Do the global databases, the Chinese one, the PBDB, do they make any sense? Probably we have to fuse them, and I'm sure that this will be done in future. So if we have now our curve, back to our curve, what can we now think? Well, surely here we have a problem. In the Furongian, there are simply no data in the paleobiology database. There are no data. So if in some curves that you have seen in the last days, you have something here, this is because the machines added some pixels. They upscaled the data. We published this last year in the paper, also IGCP related Paleo World, that there is a Furongian gap. There is a gap of data. There are simply 0 data. So when we have 0 data here, we have, of course, a big hole between the Cambrian explosion and the Ordovician radiation. But if you are a young student today and you want to do a PhD and you want to get a job, why should you work in the late Cambrian where nobody will finance you and nobody will give you a job? If you work in the Cambrian explosion, your future is sure. So we are quite sure that here a lot of people worked in the Cambrian explosion, nobody worked here. So if we can imagine that in the next years, more people will work here, and if we clearly know that a lot of people work here, so we have a lot of descriptions of taxa here, so we can imagine that we can fill this hole in the future. And actually, there is not a gap in the geobiodiversity database. They have data in the Chinese and global data set. So we can imagine that we have a straight line. And this straight line would be logical because if we look at the main trigger for the diversification of marine invertebrates at sea level. So we could imagine that the early Paleozoic had a single radiation with, of course, as Dave Harper also said it earlier, with, of course, clearly peaks that you can see in different fossil groups at different places at different moments. It's quite logical because this depends on paleogeography and many other things. So what we have today, I don't know where we are. This first picture, this is probably something that John Phillips had. Sapkowski was maybe here. I guess that we are today somewhere here. We still don't see the clear picture. And what we need to do is not to run other techniques on the paleobiology database. We need to find people who look to the taxonomy, look to the field to find the data from the places where we don't have them, like, for example, in the Furongian. And maybe we will get a picture. But I'm sure that the picture will never be totally clear because we don't have a complete fossil record. So just some conclusions. We have sufficient grounds to indicate that there was a single long-term radiation. And here I'm talking about marine invertebrates, not the other groups. We are talking about maybe 2% of the things that were on Earth or in the oceans. Nobody knows what's going on with major groups. We had to talk about calcium microbes. We don't know what, we know nothing about them. The phytoplankton, which is more than 60% of the biomass in the oceans, we have no idea. Everybody is focusing on a very little part, which are the marine invertebrates. The Cambrian explosion in terms of biodiversity is clearly an artifact, and this is due to the taphonomical conditions. There is clearly a Forongian gap, at least in the PBDB. The PBDB is far from complete, and it should not yet be used as a single standard, as other people say it clearly in, for other intervals. And so far, we have no geological event that has been recognized in the Ordovician. So this brings us to maybe a new consideration. We should call all this, as suggested by Birger Schmitz, an expansion of diversity. And with this, I thank you for your attention and take any questions if there is some time remaining. Thank you.
Yeah, thank you, Thomas, for the inspiring talk. And I would love to open the ring now, actually. The thing is, we are a little late in time, but I think one question should be allowed.
Was I too long?
You were not too long, but we were a little bit behind schedule anyway, and I think 2-3 minutes will be fine, I would say. So one question. No question, unfortunately.
I have a comment if I can. Can you hear me?
Yes.
Thank you, Thomas. I love the presentation, and maybe because I'm a classical person and I'm very skeptical about all these modern ways. I can only speak from a perspective of high latitude Perigondwana. But I'm pretty sure that if you do a curve of publications, you also have a GOBE of publications in here. Because, for example, in Ibero-Armorica, you almost have no fossiliferous record and sedimentary record below the Darwinian, and except, for example, for Montagne Noire. In Sardinia, the same. In Czech Republic, below the shark formation, the same. I don't know what is the influence of this problem in the total record, but I'm pretty sure that there is a part of influence in the data. You have much more publications from the Darwinian on, and so you have this publication GOBE and data GOBE also.
Okay, I think this will stay a question, a controversial question for the next coming years, and a very interesting one, I think.
What time is it in Finland? Because I think we have still 3 minutes.
Do we have? Yeah, you're right. Yeah. Okay, good.
But I'm fine. My 20 minutes. So.
No. Go ahead.
Can I ask a really quick question?
Mm-hmm.
Hi, this is Talia Kareem from University of Colorado. Do you think that some of those late Cambrian data exist in museum collections and that they just need to be digitized?
Yes, right. I'm not sure about North America, but there are a lot of data that have to be filled in. I don't know if Rudy is now here. So Rudy Lerosé-Aubril is now at Yale. He's working on these intervals also in North America, and there are a lot of data now, and they are simply not yet put in the PBDB. And the Chinese, they have a lot of data from North China. And yesterday we had the discussion. Yes, there are museum collections, and we need to get all this in the databases. So far, the PBDB is empty. But there have been things described, but not put in the database.
Birger has raised his hand.
Yes, Thomas, thank you for a great talk. A quick question. There was a sea level drop during the Ordovician and ice age developing, and how much has it been accounted for that there might be a phase shift component in all this in this whole story? Is that something that is considered? If you get shallower waters and sea level drops, and could that explain a part of the?
Well, at sea level correlations, it's really problematic. I'm not a sedimentologist, of course, but at a very, very large scale, we can see that with decreasing sea levels, diversity goes down, and we have this in the Ordovician. For many years, Sapkowski data set showed that we have a dramatic decrease just in the Hirnantian, but now we know that the sea level decreased much earlier, and that we have also the global diversity shows for most of the groups that diversity goes down since the beginning of the upper Ordovician. Somewhere in the Sandby and Catian groups go down already. But at the basin level, if you are just working on one section in one basin, you have not necessarily the complete picture. So it's a sum that makes us a complete picture, but it's very, very complex. The GOBE is something very complex with, there is not a single answer to this. That's my feeling.
I can just add now, Birger, that we did quite a lot to compare sea level with biodiversity in the study last year. So you can look at that, the one I did with Björn.
Yeah, you had a question to me?
No, I just wanted to tell you that now it's time in Finland too.
Yeah. Okay, I wanted to. Okay, good. We can continue now. I was a little confused. Yeah, next talk will be with Ursula Toom from Tallinn, together with Ole Finn and Ole Hinz, on the Ordovician bioerosion revolution in Baltica. Ursula, are you here?
Oh, is everything okay?
Yeah, yeah.
Oh, okay, let's start then. Hello to everyone from Tallinn, from Estonia. My name is Ursula Toom, and my talk is going to be about Ordovician bioerosional revolution on Baltica. It means about trace fossils. But briefly about geological background. During the Ordovician, Baltica paleocontinent drifted from subpolar to subequatorial region. Sedimentation basin was affected by sea level and climatical changes. Early Palaeozoic succession in Baltica is characterized by a low rate of sedimentation. Succession contains numerous sedimentation breaks and hard grounds.
Ursula, one question. Do you have slides? Maybe I don't see it. I'm sorry.
You don't see, or they all can see how it is?
You can't see it all.
You all
We
can't
only see you, Ursula.
Oh, I didn't. Oh, okay. Okay, let's start.
Not that it's a problem, but if you
I didn't share screen. Sorry. Share.
All of us complicated.
No.
Now it's perfect.
Now it's perfect. Okay. I previously asked from you. You said everything is okay.
Okay.
I'm sorry. Okay. Let's again. My talk is going to be about bioerosional trace fossils and about bioerosional revolution on Baltica. Here is a little bit about background. During Ordovician, Baltica drifted from subpolar to equatorial region. Sedimentation basin was affected by sea level and climatic changes. Succession in Baltica is characterized by low rate of sedimentation. Low rate of sedimentation, it's very important. Succession contains numerous sedimentation breaks and hard grounds. From Cambrian to early Ordovician, the sedimentation was siliciclastic, but from middle Ordovician, in middle Ordovician succession, this is represented by cool water and temperate carbonates. For upper Ordovician are characteristic tropical carbonates. During the Ordovician period, the western part of Baltica was covered by shallow sea. The succession is rich in typical Paleozoic shelly faunas. The term bioerosion was introduced by Neumann in 1966. Bioerosion is the destruction and removal of consolidated mineral or lithic substrate by the direct action of organisms. It may be mechanical, chemical, or combination of them. 12 phyla of animals contain marine bioeroders. Microscopic fungi and algae, sponges, worms, annelids, bivalves, gastropods, lingulites, crustaceans, echinoids, and also fishes. In 2006, Wilson and Palmer termed out the Ordovician bioerosional revolution. It is a dramatic diversification of macro-boring ichnotaxa during the middle and late Ordovician. Wilson and Palmer listed in paper 7 bioerosional ichnogenera, but a decade later, Mangana and her co-authors listed already 11 ichnogenera. But in both papers, Baltica was just pointed out briefly. Mentioned was only 2 ichnogenera from Baltica. In 2004, Mikuláš and Andrei Dono expressed the opinion that Baltica was the birthplace of modern bioerosion. Our materials. Materials are coming from database and paleontological collections. Data on Baltic traces is managed in the multi-institutional database of geoscientific collections, which is accessible at online. There are data on individual Estonian trace fossil specimens, including images, localities, references. Also, there is library on Baltic trace fossils literature, about 400 references from Indian to recent. Made this list of Baltic trace fossils from Indian to recent with references. Also, libraries on bioerosional trace fossils, libraries on hard grounds and by traces. Materials we used for our research are from paleontological collections of Estonia and St. Petersburg. And here are our preliminary results for Baltica. Currently, from Cambrian is known 2 bioerosional ichnogenera and from Ordovician 14 ichnogenera, and also several undescribed traces. The study brings up the globally oldest finds of 10 bioerosional ichnogenera: Trepanites, Termichnos, Pinacea-cladichnos, Sulcolitus, Dendrina, Sanctum, Petroxestes, Pospironides, Rogerella, Entobia, and oldest Oichnos in Ordovician. Here is distribution of ichnogenera on Baltica, macrobiological ichnogenera. In addition to classical bioerosional traces, is included occurrence of Balanoglossetes. In Baltica, the trace maker of this ichnogenus demonstrated the ability to bioerode. Represented is a wide scale of trace makers' behavior. Dwelling and feeding traces are common. Also are represented predation, fixation, and bioclaustration traces. Distribution of bioerosion is represented by 2 curves. Blue curve is the number of macrobioerosional ichnotaxa is here, and orange curve here is curve of different bioerosional structures for the better characterization of the volume of bioerosion in region, include different microbioerosional structures, bait traces, and grazing structures. It has to be noted that the bioerosional diversity and shelly fossils diversity curves on Baltica are broadly similar, but scales are very, very different. From the German Ocean to Florian, the echinodiversity was low. Traces are mostly related to inorganic substrates, to the hard grounds. In the Darpingian, bioerosion started to increase. New traces appeared in organic and also on organic substrates. In the Darwinian and Sandbian took place dramatic increase of bioerosion, and the majority of bioerosional traces is related to organic substrates. How to be noticed that the bioerosional traces are missing in Hirnantian. It may be insufficient sampling, but most likely it's caused by rapid changes in environmental conditions. Sea level drop down. Majority of bioerosional traces is associated with heavy calcitic colonies, bryozoans, stromatoporoids, brachiopods, and also rugose corals. According to Weiss, Jackson, and Key in the Middle Ordovician of Baltica, around 18 of bryozoan colonies are bored. 5 ichnogenera and several undescribed ichnogenera are related to the Middle and Upper Ordovician bryozoans. Clumping behavior of the different borers and overprinting are common. The morphology and the size of traces are controlled by the size and morphology of the host. Macro borings were most common in the bryozoans, occurring in muddy fissures on sandbed. Here are presented some images of formerly undescribed bioerosional trace fossils. Here are funnel shape traces, fine sinuous traces with elongated openings here. Traces starts here from the peeled area, then ends somewhere inside of the colony. Sometimes are almost half of colonies removed here and here. But describing of new taxa is quite complicated. Most of the structures are hidden inside of colonies. According to the exterior view, it is impossible to figure out what are inside. Healed injuries are known since Cambrian. From Cambrian of Baltica, they described from Sweden and also from Estonia. From Ordovician of Baltica, healed injuries described from gastropods, cephalopods, and brachiopods. Quite nice systematic works has done in Sweden. In Estonia, healed specimens have received less attention, as predators are for the Ordovician discussed mollusks, cephalopods, and also drilling gastropods. Ordovician invertebrate bite traces are globally rare. Here we have images of Sandbian 2 bite traces from Baltica, and they demonstrate 2 different types of bite marks and also different trace makers. Ichinofacies is an assemblage of trace fossils that provide indication about the environment that the trace-making organism inhabited. 3 substrate controlled ichinofacies are described from marine sediments. Glossophangitis ichinofacies, it develops on firm ground. Trepanitis ichinofacies on hard grounds, and Gnatnichnos ichinofacies on board shells and boulders. Glossophangitis and Trepanitis ichinofacies are known from Paleozoic, but the Gnatnichnos ichinofacies is previously reported since Jurassic. The research is described by shallow tear structures, grazing structures, fixing structures, edge attachments, and our research bring up presence of traces characteristic for Glatichnus ichnofacies in the Ordovician of Baltica, traces like Rogarella, Podichnus, and also unnamed grazing traces. The rapid diversification of bioerosional traces in the Ordovician of Baltoscandia was coincidence of multiple global and also regional factors. The major global factors were the seawater chemistry and oxygenization, also stability of the sea level, and increasing phytoplankton availability. The main regional conditions supporting the bioerosion were the warming climate and nutrient-rich, well-oxygenated Eberic Sea. Sunburn is characteristic by high diversity of macro and multifaunas in Baltoscandia, and by the appearance and rapid diversification of rugose corals and echinoid. Tarmo Kiipli and his co-authors associated with rise of bioproduction with seawater circulation and also coastal upwelling. The diversification of bioerosional trace fossils in Baltica is strongly correlated with the development of different organisms possessing heavy calcite skeletons and low environmental stress. But the diversification of bioerosional traces in Baltica is not related to the reef's developments. At least conclusions. Increase of macroborings ichnodiversity in Baltica was significant. The bioerosional trace fossil richness in Baltica is similar to body fossil diversity. Research will bring up new ichnotaxa. Also, presence of very shallow grazing traces of Glatichnus ichnofacies in Paleozoic. Roots of the Ordovician bioerosional revolutions are in Baltica. Baltica paleocontinent was a key region for the evolution of bioerosional trace makers. I am grateful to all colleagues for sharing research papers and for access to the collections. Also, I am grateful to my co-authors, Ola Win and Ola Hintz, for the support, and most of all, to Gennady Baranov for the nice photographs. And thank you for the attention.
Yeah, thank you, Ursula, for informing us about this important aspect of the GOBE. Very nice talk, and I'm sure there will be questions, probably.
Okay, thank you.
Any question?
Yeah.
Okay. Can I ask about the entopia you have? Because I think that would be among the earliest records of boring sponges.
Yeah, it's made by sponges, and before was reported from Devonian. And it's this is our materials for Katian.
Yeah, that's wonderful. And do you have any spicules inside the borings as well?
No, it's quite complicated to collect new material. In this summer, I tried to collect new material.
Oh well, hopefully one day. But lovely talk. Thank you.
Thank you.
Maybe I have one short question about the Hirnantian lack of data. What do you think? What is the reason?
We have discussed this this question, and I think it's quite quick sea level dropping down quite quickly. but I looked over all what we have, all fossils in collection material to find Tryponites, because Tryponites is so common in Estonia and I didn't find anything.
Very strange.
Yeah, very strange. I have to agree with you. It's really strange, but so it is. We have to try more.
Okay, good. I think at this point I have to thank all of our speakers. It was a wonderful session. Went good, I think, and I hand over to Christian, I think, and because we will have after the coffee break laboratory walk, however that will be.
Yeah, it's actually right now. So during the coffee break, I will advise all to stay seated, because we will go live to Birger Schmitz laboratory, and yeah, he will give us a tour. So Birger, are you ready?
I'm here. Do you hear me? You hear me?
We hear you. We hear you.
Thank you, Christian. I'm very glad that that we agreed on this, because this is such a nice thing, the first video conference and that I've participated, and we wanted to try to do something like more live, and we came up with the idea that I show you around a little bit in the Astrogeobiology Lab. We will start here in our office space, and then I will give a short, unfortunately it has to be a short PowerPoint presentation, and then we will go to the lab and show it. I just want, this is the office space of our lab. All the people are in the lab waiting for me to come with the camera. But most important here is, let's see how this works. On the floor here, this was something I've never done before. Yeah, here we have a complete profile of the Telstein event. So if anyone wants to study the Telstein event, including the echinoderms, it's on the floor here in our lab. You don't have to go to Kinnekulle, you can sample the entire Telstein event here. The section continues down here, and at my foot here, there is a marking. This is the level where the L-chondrite parent body breakup event. I have to practice this. This is the first time. So now I will share the screen, and I give you a short introduction to what an astrogeobiology lab is. And it will be quick because, share screen. Okay, do you see the PowerPoint presentation?
No, we still only see you.
Shit. Share screen. Okay, I just get your screen all the time. So. It just jumps up to I did this yesterday.
Maybe
is it something that you are on there, that you have the screen, Christian? Because it just jumped.
We only see you, but maybe if you open the presentation and then click share screen.
That's not possible, sir. Shit, what's the heck here? I'll close down. I did this yesterday and it was no problem at all. Share screen. I continue to push share screen and it doesn't happen. What's the... Sorry if I will use rude words here.
Now it works.
Okay, sorry. Okay, the Astrogeobiology Laboratory. What can 25 tons of rock and 50,000 liters of hydrochloric acid tell us about the solar system and of life? Astrogeobiology is about connecting the histories of Earth and space. Like we would like to find the signature of the galactic year in the geological record, not only which fossils that live. One of our most important discoveries here in the lab, and with which it all started, is the breakup of the L-chondrite parent body that I talked about on Monday. And I want to correct, I was signing up for Tomas Želvys fan club until he said that there was no geological event in the Ordovician. I would say on the contrary, that the most important, the most dramatic, the most violent, and the most energetic event in the solar system the last 500 million years was this event, and the evidence is quite strong. And I talked about this on Monday. We found more than 100 fossil meteorites that are all L-chondrites, perfectly preserved in terms of texture, but there's only one mineral that is preserved, the chromite. And here's just a quick tour showing that a lot of planetary scientists now go to a quarry. So these are planetary scientists from the ETH that found a fossil meteorite in the wall of the quarry. This is planetary scientist Alan Hildebrand. Also, there was a meteorite in the wall that day when they came. When Walter Alvarez came, there was no meteorite in the wall, so we had to place one there. And then it was impossible to travel with him in Sweden because we have Ordovician limestone floors everywhere, and he was creeping on the floor trying to find a fossil meteorite. But what we work with here in this lab is actually extraterrestrial chromite grains. For every large meteorite that falls on Earth, there are thousands of micrometeorites. And they contain these chromite grains. To the left, you see a recent Antarctic micrometeorite with a chromite grain. When this falls on the seafloor, everything dissolves except the chromite grain. In the middle, you have an Ordovician extraterrestrial chromite grain recovered with acids, and on the right, you have a 3D image of olivine inclusions in Ordovician extraterrestrial chromite grains. So we developed this in order to determine when did the LCPB breakup take place. I showed this slide on Monday. We find almost no chromite here in the lower part, 15 grains in 791 kilogram of rock. And as soon as we reach this level, we find 2 to 4 extraterrestrial chromite grains wherever you take a sample here. So by today, we have expanded our approach, and we have now studied 18 time windows in study. It's the red stars in the figure here. And we have recovered more than 4,000 extraterrestrial chromite grains from about 10,000 kilogram of limestone. Down here, you have the GOBE. And we aim for the first reconstructions of the variation and the flux of meteorites in deep time. So why do we want to know about this? Yeah, we would like to establish the history of the asteroid belt from Earth sediments, or the history of the solar system through studies of Earth sediments. They're out in the asteroid belt between Mars and Jupiter. There are these huge asteroid families that all represent major bodies that broke up in collisions. And astronomers, they try to date the formation of these asteroid families by backtracking the orbits to a central point. And of course, we try to find the signatures of these breakup events in the sediments, because when the bodies broke up, a lot of material would have been sent to Earth. So here's just a quick example. I go through it very, very quickly. In 2007, Bill Botke proposed that there was an asteroid breakup 160 million years ago and in that breakup were the pieces liberated that then was resulted in the Chicxulub crater and the Tycho crater. So we went to a section in the Apennines, Walter Alvarez and Jan Smith. They told me about this section, and it spans 10 million years of the early Cretaceous, and it's extremely clean limestone. So it was the perfect place to search for the signature of the breakup of the Baptistina asteroid family. So this is, our samples are quite big. So this is how you take a 300 kilogram sized sample of this limestone. And to today, we have dissolved 1,652 kilogram of this limestone. Walter Alvarez and Jan Smith helped out in the section. Here you see my daughters being very happy to help their father with geology work. In 1,652 kilogram of rock, we found only 2 grains, extraterrestrial grains larger than 63 micron. Compare that with 2 grains per kilogram after the breakup event in the Ordovician. So this is how it looks when we ship 2 tons of rock to Sweden. And this is very boring. This just shows how we use elements and oxygen isotopes to determine, we can determine what is the origin of what type of meteorite does each extraterrestrial chromite grain represent. And then you write a paper that you can read more about in Geology 2017. Meteorite flux turf in the early Cretaceous as reconstructed from sediment dispersed extraterrestrial spinel. Here, just to give you a perspective on the mid-Ordovician, this little diagram shows the 3 types of ordinary chondrites, the distribution between them. In the recent meteorite falls, the proportions is 42, 47, 11. In the mid-Ordovician, before the L-chondrite breakup event, it's about 1/3 each. After the breakup event, it's 100% L. In the early Cretaceous, it's about the same as today. No increase in LL chondritic grains, which would have been the case if there was a signature of the Baptistina asteroid breakup, because the Baptistina asteroid is an LL chondritic body. So the LCPB breakup, a unique major solar system event with big letters here, Thomas. I argue that there was, at least we know of, one event. And in our Science Advances paper in 2019, we have bed by bed, we have located exactly which stratigraphic level it corresponds to. And this is what I mean. I guess this is what you mean by high pixel approach. We can locate this bed with the help of our laboratory and our methods. We can locate it to within a resolution of centimeters, and we can then relate it to other things like sea level curves, like biotic changes. I argue, and Christian might argue against me, but I argue if you extend this red line to the Luna section, where Rasmussen et al. Did their study in 2007, I would say that this red line comes out approximately here. We need a further high pixel. We need to get even further down in high pixels in this section to confirm this. But this is my strong belief that this often in this meeting, I've often seen the change from down here in the Dapingian up to here, like a straight line from here up to there. But if you look in this diagram, and I'm not an expert on it, but it at least looks as if it's 2 steps. And to me, it looks, or I believe, I bet Christian $1 that this is where we have the event, but we can continue that later. So we have sent 1 ton of rock from the Pacifica quarry south of San Francisco, one ton of limestone, and we're searching for chrome spinel grains from the Tycho crater that we know formed about 108 million years ago. And so we have searched this section. We've still not found anything. Our dream, or our vision, that we hope we will get funded and work with this the coming years, is to try to find, is to use the fact that in the chromite grains, there is also cosmic ray signal the chromate grains were in micrometeorites that were irradiated by cosmic rays, galactic rays, when they were out in space. And that means that chromate grains from time periods when we were in the spiral arms would have a stronger cosmic ray signal than chromate grains from other periods when we're not. So, and with this, we might be able to establish how many spiral arms there are. We don't know that. Astronomers don't know that. We might determine when did Earth enter the arms, and maybe even answer the question where we were 470 million years ago in the galactic orbit. And now let's go to the hydrochloric acid lab, where our research engineer Fredrik will guide us. Can you switch to the camera in the lab, Christian? I will go to the lab.
Welcome everybody to the Bioerosion Laboratory, and we are now in the core of the lab, the hydrochloric acid lab. Another 3 units building up this lab. It's the hydrofluoric acid lab, the sieving lab, and the polishing lab. But now we will have a look in the hydrochloric acid lab. And here is one fume room instead of a fume hood. And here we have this setup with a 520 liter barrel with a lid, sealed lid with lead weights on top. We are putting the sample, a 100 kilogram sample of limestone in this barrel, and then we pour 200 liters of water and 200 liters of concentrated hydrochloric acid in this barrel. And then it reacts, and during this reaction we have a tremendous pressure from the carbon dioxide, and this carbon dioxide is led through this hose down to a scrubbing device with sodium hydroxide. Right, so after 24 to 48 hours, the calcium carbonate is dissolved, and we have a residue of clay minerals and siliciclastics. And now we have to go on to the next step of pouring it to smaller containers. For that, we have. So
how much remains, Fredrik, of 100 kilogram limestone?
It differs, but around 25 to 100 liters is remaining.
But how much in kilogram? 10% of the limestone remains.
Yeah, something like that. Yeah. All right. So we have this device where we pouring a residue with it like this into smaller 5-liter jugs like this one, and now we have to go further in the next lab to the sieving lab, and Birger is pointing it into this room. It's actually a neutralization room where the residue, the acid residue, is poured, and then we have some limestone powder. We neutralize that, and this in turn is pumped out to a quite impressive pipeline system running all the way down through the corridor and to the outside of the house where it's picked up. Okay, let's go to the sieving lab. So now we're in the sieving lab, and here is Faisal standing and sieving. I have built 2 sieving machines for this. So we're wet sieving the about 10 jugs of material. And when it's done, we have something like this left. And now we have to treat this as well. So we have to go to the next lab, the hydrofluoric acid lab, to get rid of this.
Everything okay, Faisal? Good.
All right. So let's go to the hydrofluoric acid lab. And this specialized hydrofluoric acid lab, as you can see, there are some dangerous stuff in here. Hydrofluoric acid is very, very dangerous and poisonous. So there are really strict regulations when working in this lab. So let's go in. And here is Eleanor working in the HF lab. And how's it going, Eleanor? Everything is okay? Yeah. So here we can treat quite a lot of material. So when this is done.
So what do you like working in here, Eleanor? You like it in here? Okay, great.
So when this is done, from all this, from 100 and 110 kilograms of rock, the residue, the end product after the HF lab is this. And what we're doing in the next step is actually putting it under a stereo microscope and picking the chromite grains out. All right. So that's our little trip, and I hope you're all right. And if you're interested, you can you always come here and have a more closer look in the lab.
Bye-bye, Eleanor. Hope you'll enjoy it.
Okay, Birger, thanks for the tour.
Okay. Am I on? Or?
You're on, yeah.
I'm on the screen, or?
Yeah.
Okay, so I don't know if we have a few. Okay, welcome, Fredrik. So where did you get that nice haircut?
Yeah, amazingly, I found this lady outside the lab. She said, "I cut your hair for 50 kroner," so I couldn't resist.
Okay, so the tour in the lab was pre-recorded, just for the record. So sorry for the technical problems. It was the first time we did this, and if anyone has any questions, and if there is any time left.
Well, I can also say that you can just all ask questions for Birger now, but otherwise we will reconvene in 10-12 minutes time. But it was a nice tour, Birger, and it's very interesting to see that you have basically a core line there through the whole Tailstein event and also the whole succession. How on earth did you manage to get that out of the out of the rock in the field?
We have as you know, we have a close cooperation for 25 years with the quarry workers of the Torsberg quarry. So it's basically the wall in the Torsberg quarry. As you know, for 25 years we have cooperated with them and done this systematic search for fossil meteorites on an Ordovician seafloor, and we have a very good relation to them. But if anyone wants to work with the Tailstein, it's here. So.
It looks certainly great. Yeah. Any questions? So on the chat, Gustavo is asking, thanks for the presentation. Have you tried to recover extraterrestrial chromite from shales?
Yeah, actually, we have just submitted. Fredrik Terfelt has worked before in the Cambrian, and he has taken the lead on extracting extraterrestrial chromite grains from the alum shales, and we have been very successful. So we will publish that in whenever they accept the paper for publication. But it has to be one thing. It has to be condensed shales. This whole thing only works with condensed sediments. You can only work with the pelagic. Otherwise, the amounts of acid that you will need are impossibly high or large. But it would certainly be interesting to. If anyone has a condensed section somewhere across this equivalent to the Tailstein bed, we would of course like to have more data testing if the breakup really led to a sea level drop. We have preliminary data from China. We can of course reproduce the breakup signal, but it's always a problem. Sea level records, as you know, they are difficult to interpret. I think the exciting thing about the Tailstein event is that it's such a clear and obvious example of a relatively fast shallowing in an environment that normally is much deeper. So.
I can just relay that a comment from Lucy, who's saying thank you. It's a really interesting tour, and this is the first lab tour she's ever had while eating a pizza.
Yeah, okay, that's the point. As long as you don't go to the restroom, it's okay with me. So during, but I think this is really an interesting concept, and we tested it here, Christian, and I hope it was of some enlightenment for everyone.
It certainly was, and it was fun. But there's like still 5. So maybe we should just get a coffee, Birger, before the
I
next
would like to
session.
get a coffee.
Okay. We break off for a second then.
But one thing. Did you accept my bet, $1? I said
Well,
I said I was.
We can take that afterwards. Should we say that?
Okay, so you don't dare take that bet. Okay.
Well, I dare take the bet, but your correlation was wrong. But we can take that afterwards.
Okay, it sounds to me you take the bet, $1. Fine. We have witnesses now. Fine. Okay. Thank you. Bye bye. Thank you for listening.